We're gonna get started. We were talking about last time balancing equations, and chapter 7, I think. So remember that when we do balance equations, the only things that we can change are the coefficients in front. So only the numbers in front. We talked about, maybe doing a table type of method is a good way to sort of organize things as you're balancing the equation. We did see a couple things that when you are done balancing the equation that you do need to make sure of. Obviously, you need to have the same number of elements on each side of the arrow. You also need to have all whole numbers. So these guys need to be all whole numbers. They do need to be the simplest set of whole numbers. So again, if by some chance you did balance an equation with maybe some larger numbers, and you can kind of divide through all those coefficients by a common number, still have a whole number. So again, in this case, you would want to divide by 2, and that would give us a plus 2b goes to our 3c. Again, that would be the properly balanced equation. So again, sometimes it does happen if you see sort of a larger number or something like that to balance it, and it absolutely could be balanced. But again, you do need to kind of just look through your coefficients at the end to make sure you can't reduce them all down and still have whole numbers. The other thing we saw at the very end last time, again, is that you can use a fraction to balance the equation. But remember that if you do use a fraction to balance the equation, you cannot leave the fraction as a coefficient, again, because that's not obviously a whole number. You do have to get rid of the fraction. So typically, if you can go shoot for a fraction here, basically, again, the number that goes on top is the number you need, is typically the number you put up on top. And usually the bottom one will match the subscripts to whatever is there. For example, I think we looked at O2 in one of them. And again, then that 2 would be kind of what you'd put on the bottom. So if you have to kind of pick a fraction, you want to not mess up the fraction per se. That is typically how you would do it. Again, number you need up on top, matching sort of subscript there on the bottom, and that will get you the right fraction. Then obviously you need to clear the fraction by multiplying everybody in the equation, not just the fraction, but everybody in the equation by that denominator that got on the bottom there. And again, at that point, if you do that, you will have a balanced equation. Any questions on any of that there? All right, so let's see here. Looking at a couple of other types of equations. Now, sometimes you will come across some equations, for example, like this one, where we do have, for example, a number of polyatomic ions on each side. So when I look at this, I do see CO3, which is carbonate on each side. I also see sulfate, which is a polyatomic ion on each side. Now, you could also, like we talked about, kind of take the same approach we did the other day, where you could make a table and go sort of element by element. But what will happen sometimes is because it's polyatomic ion and you do need to put kind of parentheses around everybody, sometimes there's a lot of like multiplying in, multiplying out. So there's a lot of chance for error. So sometimes it's a lot easier, especially if you see an equation like this, where there are polyatomic ions on each side that are the same, just to balance those polyatomic ions as like whole units rather than breaking up element by element. So what I mean by that, for example, here is I'll just start with the carbonate here. On the left-hand side, I have 2 carbonates. And on the right-hand side, I have really only 1 carbonate. So I'm just going to balance that carbonate by putting a 2 in front of it. That will give me my 2 carbonates. And when you kind of do this method, what you would want to do is whatever is attached to that particular guy, like the carbonate, we would then want to go to the sodium next. And here, by putting that 2, it does give me 2 carbonates, but also gives me 4 sodiums. And that's where I would want to go next. So I'll come over here to the left, and now I need to make my sodium into 4. And again, what that's then going to do for my sulfate is it is going to mean that I need 2 sulfates. And if I come over here to the right, I already have 2 sulfates and I'm done balancing at this point. So that's very common what will happen if you have some equations with some polyatomic ions in it. If you kind of keep them together instead of going element by element, you can still do element by element if you want, but it might be a little bit longer, maybe a little bit, again, more room for error because you got a lot of multiplying in and multiplying out. But if you kind of keep them together and just kind of balance them, what will usually happen, thank you, we just saw there, is eventually things will just sort of fall into place as you sort of balance it. Like again, by putting the 2 there in front of the sodium on the left, took care of the 2 sulfates that I needed to balance everything out. So if you do have one of these guys, again, they do need to be polyatomic ions on both sides of the arrow. They need to be the same polyatomic ion on both sides. And you need at least one in the equation to kind of do that. If you got multiples, again, in this case, we did have multiples. You could have started with either one. You could have started with the sulfate as well. Now, in some cases, it may not work out good depending on which one you choose. So you might have to go back and maybe start with the other one. But, you could kind of quickly fix it. Any questions on that there? All right, so why don't you try a few here and see what you come up with. So balance these equations, then we'll go over them. Okay, let's take a look, see how you're doing. Once again, here on this first one, I definitely see some polyatomic ions on both sides. So I got some sulfates, I have some nitrates. So again, here, I'm going to take the approach to kind of keep them together and balance them as units rather than go element by element. So I don't have so much kind of multiplying in and multiplying out. Again, in comparison of the 2 polyatomic ions, I have 2 nitrates on this side and 3 on this side. And in terms of the sulfate, I have 3 on this side and 1 on this side. So I'm going to actually start with the sulfate since it seems a lot easier to kind of do that. Only 1 coefficient to start with. You can start definitely with the nitrate if you wanted to as well. You would need a common number of 6 there and a 3 and a 2 on each side. Here we will go with a 3 here to get us our 3 sulfates. When we do this, we then want to go to whatever it's attached to. In this case is calcium, which means I now have 3 calciums on the right, so I need 3 on the left, so that's where I'm going to go next. Now that I got the 3 calciums there, I now have 3 times 2 for 6 nitrates, and that's where I'm going to go next, and I'm going to put my 2 there to give me my 6 nitrates. That also gives me 2 irons, which is exactly what I need there as well, and now I am balanced. And again, usually a lot quicker and a lot easier if you have those polyatomic ions that can just kind of keep them together in that method. Any questions on that one there? We take a look at the next one, same deal. We got some sulfate on each side. We got some phosphate on each side. In this case, the sulfate is balanced on each side. We got 1 of each, so I'm going to start with the phosphate. And I have 2 phosphates on the right. So to fix that on the left, I'm going to put a 2. That will give me my 2 phosphates. Now I want to worry about my silver that I kind of messed up there. So that's going to give me 6 silvers. I then will go to the right-hand side and turn that silver into a 6. And since I have 2, that means I need 3. That again will give me 3 silvers and now 3 sulfates. And lastly, here I can now come back to the left and I have 1 sulfate, which means I will need 3 of them. And that will also give me 3 carbons, not carbons, coppers. And that will get me to our right answer there. So again, you kind of want to balance the polyatomic ion. Once you put the coefficient, whatever it's attached to, that's where you want to kind of go next. And then whatever that's attached to, that's where you want to go next. And it's kind of go back and forth. And again, eventually things will sort of fall into place. Any questions on that one there? So again, this is an alternative approach. Like I said before, you can still do like we did before with the table. It's just going to have a lot more multiplying to do for each element because you have the polyatomic ion, those parentheses and stuff like that. Any questions on that there? All right, taking a look at the last one here. We have no polyatomic ions, so I am going to go back to our table sort of method here. And in this case, carbon, hydrogen, and oxygen. So on the left-hand side, we got 4 carbons. Right-hand side, we got 1 there. Left-hand side for hydrogen, we got 10. Right-hand side, we got 2. Left-hand side for oxygen, we got 2. And we have 2 oxygens on the right, and 1 more there makes 3. Once again, here I'm just going to shoot for what looks easiest. To me, it looks like carbon there is going to be pretty easy to balance. So I got 4 on the left, 1 on the right. So I could fix that by putting a 4 in front. Again, it does go for everybody behind it. That will give me 4 carbons. We still have 2 hydrogens. Now, in terms of oxygen, I have 8 in the first one, still have 1 in the second over there. So that's going to now give me a total of 9. At this point, I have hydrogen or oxygen. And as we talked about last time, I'm going to go with hydrogen here again because oxygen's in a couple different places on the right-hand side there. So hydrogen is pretty simple to fix. And to fix the hydrogen there, we got 10 on the left, 2 on the right. So we would need a 5 in this case. And again, that's going to go for everybody behind it. So that will give me 4 carbons. 5 times 2 is 10 hydrogens. I still have 8 in the first one, but now 5 times 1 is 5. And 8 and 5 is 13 oxygens in this case, yeah? So again, at this point, we kind of put coefficients on the right-hand side. We definitely don't want to go back and change them. This is a situation where we basically need to turn a 2 into a 13. So this, again, is a prime example where we could do a fraction. So again, to choose the correct fraction, I need 13. So that is what's going to go up on top. And on the bottom is going to match basically that number there, and that's a 2. And now I should have the correct fraction that I need. We will have 4 carbons, 10 hydrogens. And again, if we take 13 over 2 times 2, that's going to leave us 13 oxygens in this case. Now, again, it is balanced, but we cannot leave it like that because all the coefficients do have to be whole numbers. So we do need to go back through and again, multiply everything by the denominator there, which is a 2. So we're going to take everybody again, not just the fraction, and we're going to multiply everybody by 2 on the coefficients. And that will give us that'll give us 2 C4H10 plus 13O2 goes to 8 CO2 plus 10 H2O. And once again, if I did not screw up, hopefully, we should still be balanced. So let's just take a look at it here. 4 times 2 for the carbons, 8 on the left. 8 times 1 is 8. For the hydrogens, 2 times 10 is 20. On the right, 10 times 2 is 20. And oxygens, 13 times 2 is 26. 8 times 2 is 16, and 10 times 1 is 10, 26. So we are balanced in our equation there. Again, we now have all whole numbers in terms of our coefficients. Any questions on balancing equations there? No. All right. We're then going to continue on to talk about types of reactions. So we're going to talk about types of reactions and ways to classify reactions. And there's really, as we will see, kind of 3 reasons for the most part why a reaction takes place. So you can almost boil down a reaction to sort of 3 reasons it takes place. So one of the 3 reasons it takes place is the formation of a solid, and that's sometimes referred to as a precipitate, abbreviated PPT for precipitate. The second reason is the formation of water, H2O. And the third reason really why a reaction takes place is an electron being transferred. So pretty much every equation or reaction that you see, pretty much one of those 3 things are pretty much occurring. And that's really what is sort of happening to make that reaction occur. Either you made a solid, you made water, or some electrons basically transferred in the process. Now, when we talk about reactions, there are multiple ways that you could classify the same reaction, but pretty much all reactions fall under 2 sort of umbrellas of reactions. And we're going to talk about those 2 types of reactions. And the first type of umbrella reactions are what are known as double displacement reactions. And double displacement reactions, as we will see, basically has this setup. It always is 2 ionic compounds. So you have a positive guy and a negative guy together, and a positive guy and a negative guy. And always when you have that combination, what ends up happening is these two guys basically switch partners and they make new ionic compounds on the other side, A and D here in this case, plus C and B in this case. And this is your classic double displacement reaction. And as we will see, what will happen in some cases is one of these guys may make a solid. And that would account for one of the reasons why the reaction took place. Or you may make actually water as a result of that, which is basically the second reason why a reaction takes place. So double displacement reactions are kind of like a big classification of reactions to which take care of two of the three reasons really why a reaction takes place. Either you made a solid or you made basically water. The other type of reaction that we'll talk about are what are known as redox reactions. And redox reactions are essentially all about the third reason, an electron being transferred. So an electron transfer is what occurs in a redox reaction. Now, underneath each of these kind of big classifications, you could classify the reaction in a more specific way, depending on what's happening. So again, as I said, you could have basically the same reaction in multiple ways of sort of classifying the same reaction. So let's take a look at each of these types of reactions here and maybe more specific ones. So oxidation reduction reactions, these are basically what are known as redox reactions. And oxidation and reduction mean a couple different things. Oxidation means that you lose electrons. Reduction means that you gain electrons. So sometimes people like to remember that. Leo the lion goes grr. Loss of electrons, oxidation. Gaining of electrons, reduction. Some people are fond of the oil rig. Oxidizing is losing. Reducing is gaining. You put Leo the lion on the oil rig and he goes grr. You don't have to choose. You just use all four together there along the way. There's actually other definitions of oxidation and reduction that we will talk about, and we will see actually more when we get to organic chemistry. But in sort of inorganic chemistry or general chemistry, the electron sort of definition is the one that we think about the most. They always sort of occur together. So if somebody gets oxidized, somebody else gets reduced. And the nice thing about that is if you can figure out one, then the opposite thing is happening to the other thing. So you really just have to figure out one, and then basically the opposite is occurring. So how do we know, for example, if something is being oxidized or reduced? We could think about it, what happens when somebody gets oxidized or reduced. We could also just use a basic number line to help you out. So right here are positive numbers, to the left are negative numbers, right? And when you lose electrons and you go through oxidation, because you lost electrons, you now have more protons than electrons. That means that you actually become more positive. So if you look at the charge of something, an element on the left-hand side of the arrow to the right-hand side of the arrow, and it's moving like in this direction, a more positive direction, it is going through oxidation. Now, when you gain electrons, you actually become more negative than you started with because you gain those electrons. So you now have more negative electrons than positive protons. So you actually become more negative. So if you look at what's known as really the oxidation number of an element on the left-hand side of the arrow to the right-hand side of the arrow, or the charge, if you want to think about it that way, and it's becoming more negative, like moving on the number line in this direction, you are going through reduction. So how does that happen? Let's just take a look at an example here, like sodium and some chlorine. And it makes a little sodium chloride. I'm going to balance it like I'm in chemistry class here, maybe. There we go. So when we look at this reaction, remember that as we talked about previously, when you take an element that is by itself off of the periodic table, it is not combined with anybody else. It really has no charge, right? So the sodium over here has really no charge and it's neutral. The chlorine is a diatomic molecule. That is how it naturally comes when it's by itself. It also has really no charge either. But when those two come together, that is when they gain charges, because now we're putting together a metal and a non-metal. So that is when they actually gain a charge, and our sodium ends up at +1 because it's group number 1 on the periodic table, and chlorine becomes -1 because it is group 7 on the periodic table, right? And it's got a -1 charge. So if we wanted to figure out in this particular case, who is being oxidized and who is being reduced, once again, this is how the number line works. I'm going to take my sodium to start with, and my sodium started at 0 to begin with on this side. And on this side, it really is Na plus, which means it's +1, which means if I were going on the number line, my +1 is to the right there, and I am going in the positive direction. That means that this is going through oxidation, and that means that this sodium is actually going through oxidation in this particular case. Now I could do the exact same thing for my chlorine. My chlorine on the left-hand side of the arrow is starting at 0. I'll just go below. And on the right-hand side of the arrow, it's ending at -1, which means it is actually moving in the negative direction, which will tell you that it is going through reduction. And this guy is going through reduction. And that is also always the case. As I mentioned before, they always occur together. So what is really happening in this case is this sodium is sending some electrons over to the chlorine. The chlorine is picking it up, and that is the basis of a redox reaction. It's the transfer of electrons. That is the third reason why, again, a reaction takes place, is this transfer of electrons is basically what's happening in this particular case. Any questions on that? By the way, the good news is we know that metals typically form what type of charge? They typically form positive charges, yes? And nonmetals form negative charges. So whenever you have an ionic compound, the metal should always be the one being oxidized because it's going to give away its electrons. The nonmetal is always going to be the one that gains electrons because it becomes negative. And so when you have an ionic compound, it's super easy to figure out because the metal should be oxidized and the nonmetal should be the one that's being reduced and gaining the electron. The number line could also be helpful, though, in case you maybe are comparing something that is metal, maybe on both sides. So, for example, if I had an iron with a +3 charge on the left and an iron with a +2 charge on the right, is that iron going through oxidation or reduction? Take a moment and try to figure it out there, maybe through the number line, and see what you end up with. All right, so what do we think? Oxidized or reduced? It is reduced, right? And the way, again, you could do it is the charge on the iron on this side is +3, which would be around here on our number line, right? It ends up being +2, which means it has to be moving in this direction to the left. Left is negative. Negative means it is going through reduction. So it is being reduced in this case, or going through reduction. Any questions on how to do that there? So essentially, if you are becoming more positive, you're going through oxidation. Becoming more negative, you're going through reduction. All right, so we just talked about that basically here. The above reaction, again, is a redox reaction or oxidation reduction reaction. Here's another example, right? If we take a look at this, that is magnesium by itself. Again, we'll have basically no charge or oxidation state. Oxygen, that is naturally how it comes. Once again, when those two come together, that's really an ionic compound here. That's group 2 magnesium +2. That is -2 group 6 oxygen, like we did with naming. Once again, if you take a look, you can figure it out, hopefully. And we'll take a look at magnesium starting at 0 on the left, ending at +2 on the right. So the magnesium here is going through oxidation. By the way, as soon as I figure that out, I already know that is reduction because it always happens together. So you don't really have to figure out both. You just need to figure out one. But we can still do it for the oxygen. Oxygen started at 0 and ends at -2 in that case. again, heading in a more negative direction, being reduced in this case. By the way, things that are being oxidized are reduced is always on the left-hand side of the arrow. The reactant side of the arrow is where you find the things going through oxidation or reduction is basically where you find that. We also know, right, from what we just talked about, that's a metal, that's a non-metal. So again, my metal should go through oxidation, and my non-metal in this case, especially in the formation of an ionic compound, should get you a reduction for your non-metal. Any questions on that? So this would also be classified as a redox reaction. Now, there are a couple of other sort of definitions of oxidation reduction, and we'll talk a little bit about it here, although we won't probably see it too much until we kind of get to organic a little bit more. And that is when we involve nonmetals, which is what happens with in organic chemistry. It's all about nonmetals pretty much. When we talk about oxidation, it really has sort of three definitions. It is the losing of electrons. It is the gaining of oxygen from reactants to products, and it is the losing of hydrogen from reactants to products. So those three definitions are three definitions for oxidation. Again, these two we will see more in organic than we will probably in this chapter. But that is, again, something that we kind of see in organic chemistry a little bit down the road. Reduction here, again, gaining electrons, losing oxygen as you go from reactants to products, and gaining hydrogen as you go from reactants to products. So again, if we take a look at this, we take a look at the sulfur here as it goes from left to right. It has two oxygens and it gains some oxygen. So the sulfur here is being oxidized. And the oxygen here is actually being reduced in this case. Now, when we look at the bottom one here, the copper has oxygen, does not have oxygen on the other side, so it lost oxygen, which is a definition of reduction. Yeah. And if that's going through reduction, that means the hydrogen here is being oxidized. In the case of the second one, we actually have a metal, so we could actually look at the metal, the copper. The copper on the left-hand side is copper 2. On the right-hand side, that is copper with no charge. So it's going from +2 to 0. So again, if you did your number line where your copper is starting at +2 and ending at 0, which is going in the negative direction and going to be reduced, which is what we got there as well. So in the case of the second one, since we still had a metal, you could kind of still do it that way as well. Or you could do it with the oxygen, hydrogen. Again, in organic chemistry, since it's basically all about nonmetals, carbons, oxygens, hydrogens, we oftentimes will use the kind of oxygen and hydrogen definition for oxidation and reduction. But in kind of regular non-organic chemistry or inorganic chemistry, the gaining and losing of electrons is very common. And hydrogen, same idea here. Carbon went from having hydrogen to not having hydrogen, so it lost hydrogen along the way. So again, the carbon here would be oxidized. By the way, the carbon also lost hydrogen but gained oxygen, which also tells you it was oxidized as well. So they all should agree with each other, no matter what sort of definition that you choose. So this would be oxidation or oxidized, and this would be reduced in this case. All right, so as I mentioned before, those are the three sort of reasons why a reaction takes place. And as I said before, our kind of double displacement reactions kind of take care of these two, and our redox reactions basically takes care of the transfer of electrons. So let's talk about more specific ways of classifying reactions. So the first type of reaction we're going to classify is a synthesis reaction or a combination reaction. This falls under the big umbrella of a redox reaction. So a more specific type of redox reaction is something known as a synthesis or a combination reaction. It is pretty much what the name sounds like. It is two things that make one thing, basically, right? It's kind of comboing together, putting them together. So here we have two things make one. That is a synthesis or combination. Again, two things make one, synthesis or combination. We saw this earlier that is still a redox reaction, and so is this one. The hydrogen here is 0 on the left. The oxygen is 0 on the right. The hydrogen on the right-hand side of the arrow is +1 and -2 for the oxygen there in water. And that again means if you're looking at your number line to verify, hydrogen is starting at 0 and ending at +1. So it's becoming more positive. So it is the oxidation occurring on the hydrogen. The oxygen is starting at 0 and ending at -2, becoming more negative, and is the oxygen that is going through reduction here. So the sort of big classification of this type of reaction is an oxidation reduction reaction or a redox reaction. A more specific way of classifying this reaction is a synthesis or a combination reaction. Any questions on that? Now, the opposite of that type of reaction is a decomposition reaction. And in a decomposition reaction, we're basically taking one thing and breaking it apart into two or more things. This is also under the umbrella of a redox reaction. So this is a redox reaction. Again, a more specific way of classifying this one is a decomposition reaction. Again, one thing makes two, one thing makes two. This is our water there. If we run an electrical current across water, we will break water up into its elements. And in this direction, where we take water and break it back into its elements, we're actually going from +1 for the hydrogen, -2 to 0 and 0. So again, in this direction, breaking it apart, the hydrogen is starting at +1 and ending at 0. So it's actually the hydrogen in this case that is getting reduced. And the oxygen starts at -2, which would be over here, and ends at 0, which is becoming more positive, and is the oxygen here that is getting oxidized. Is the opposite of when you put it together, and it's because it's the opposite reaction. So the opposite thing is happening in this case. Same thing here. That's a +2, -2 to 0 and 0. So again, it is also transfer of electrons are happening in this case. So again, the big classification of this type of reaction is a redox reaction, transfer of electrons. More specific classification is a decomposition reaction. Another type of redox reaction is a single replacement reaction. Again, this also falls under the big category of redox reactions. And in this case, you basically have one thing and an ionic compound. So you got something that's like ionic. And if this is a metal, it will have no charge to begin with. But when metals do gain charges, they actually become positively charged. So what happens in this case is the metal will actually come in and kick out the positive guy in this guy. And then when he does that, it's actually going to gain a positive charge when it kicks that guy out. And it will then make a new ionic compound on the product side. And the guy that gets kicked out will actually come and get kicked out and end up with no charge. And the reason the charges change is there's electrons being transferred in this case. So that's essentially what's happening here. And that's why, one starts with no charge, ends up with a charge. One starts with a charge and ends up with no charge. Again, it's that transfer of electrons that's basically occurring here to cause that. Now, you could also do this if the first guy here was actually a nonmetal. And once again, the nonmetal here would have no charge. But when nonmetals gain a charge, they actually become negatively charged, which means in this case, it would actually go kick out the negative guy if you started with, say, like chlorine or bromine or some type of nonmetal like that. And it will make a new ionic compound because at that point, it's going to gain a negative charge and then end up with whatever gets kicked out with no charge in this case. Now, in order for this reaction to actually take place, whatever is coming in needs to be more reactive than what is replacing. So whatever comes in more reactive than what it is replacing. So for example, the one we have here, this is zinc with no charge. That's hydrochloric acid, which is a positive negative thing. When zinc comes in, it kicks out the hydrogen. When hydrogen gets kicked out, it becomes molecular hydrogen, which is hydrogen gas. If you do this reaction, you'll see bubbles, and that's the hydrogen gas bubbling, basically. And the zinc will then gain a positive 2 charge to match up with our chloride, which is -1. And this guy will end up with no charge in this case. So again, in this situation, we're getting this transfer to occur, and this reaction will occur. And that means in this case, zinc is actually more reactive than hydrogen, because this reaction would actually occur. Now, if you try this exact same reaction with our friend copper, you will get no reaction occur. And that means copper is less reactive than hydrogen. It cannot replace it. There is actually a list that kind of tells you, like, which one's more reactive or not. And it's what is known as an activity series. And an activity series is basically somewhere there's hydrogen, a bunch of elements above it, a bunch of elements below it. And anything like higher on the list will replace anybody lower on the list. And anybody lower on the list will not replace anybody higher on the list. So for example, copper would be below hydrogen and zinc would be higher than hydrogen. So zinc would replace hydrogen, but copper would not do that. So that's a single replacement reaction. Basically, one guy comes in, kicks out the other. And again, we're still ultimately having electrons being transferred, which is why this is also, again, a redox reaction happening here. And it is more specifically classified as a single replacement reaction. Any questions on that there? Now, a precipitation reaction is a specific classification of a double displacement reaction. So this one is not a redox reaction. There is no electrons being transferred here. This is a double displacement reaction. And you always know when you have this set up, like I said earlier, an ionic compound, positive, negative, 100% of the time, they're just going to switch partners on the other side. And you'll get A and D and C and B here. And in a precipitation reaction, what happens is that switching will create a solid that's formed, which is known as a precipitate. So if I look at that, that's a positive negative guy. That's a positive negative guy. And again, they're just going to switch partners to the other side. And when they do that, it is going to be the potassium hooking up with the nitrate, which makes our potassium nitrate on this side. And then it's going to be our barium hooking up with our chromate, making our barium chromate on this side. So this is a precipitation reaction because this guy is going to form a solid. And again, a solid is sometimes referred to as a precipitate, and that's sometimes abbreviated with PPT. If you see that, that just means a solid or a precipitate. Now, one really important thing that people make a mistake on with this is, for example, let's just say they had let's just say they have this and they had to write what's on the other side. And it's really important that if you have something like this where you have to kind of predict what's on the other side, especially with these double displacement reactions, that you just take the basic ions of what makes up each of those guys on the left-hand side, and you want to make sure you get the right formulas down first. And then once you have the right formulas, then you should balance it. Too often people will write the wrong formulas on the right-hand side of the arrow because they're trying to balance it while they write the formulas. And you should never do it that way because you'll get the wrong formulas and probably never balance. So you always want to get formulas first, regardless of the balancing part, and then balance it. What I mean by that is when I look at potassium chromate, this is basically an ionic compound, which is made up of 2 ions. It's made up of K+. It is not made up of K2+, right? Because there is no K2+. K is group 1, which is potassium, is +1 charge. The 2 means you have not one, but you have 2 of them, basically, is what that 2 means, right? Chromate is CrO42 minus, which is a polyatomic ion. Over here, this is barium nitrate. Barium is group 2, which is Ba plus 2. And nitrate is NO3 minus. Again, I am not concerned at this point about the extra 2s that are there or anything like that, because I definitely want to make sure I get the right formulas first. The nice thing about this type of reaction is basically we just need to switch partners. So this guy is going to end up here, and this one's going to end up here. The approach you should take on this is what we talked about with nomenclature, which is when I put a positive guy together with a negative guy, the overall charge needs to be 0, right? And that's what you should look at this point. You want to take the basic ions and then put them together. That is why when I take K plus and -1 here, I get KNO3. I do not get like K2NO32 or anything like that, right? That is the proper formula for when those 2 ions come together. That is also why when I put this guy together, which is +2, with this guy, which is -2, I just need 1 of each of them. And that is how I get to these actual formulas here. Now that I have the actual formulas, now I should balance it by changing the coefficients. And that is the order in which you want to do it. Very common, like I said, when people have to kind of write what's on the right-hand side of the arrow and it's not given to you, they want to kind of do both together. And it's like, for example, this is a common outcome for a lot of people when they have something like this. They write K2 and O3 2, right? And just kind of keep the 2s because they want to balance it. There is no such thing, yes? So again, you want to make sure that you get the proper formula first. And now you could go back and go, oh, all right, well, I got some polyatomic ions now. I need a 2 there, and maybe that's all I need in this case. And now I'm balanced in this case. So proper formulas, then balance, don't do them together. And this is always how a double displacement reaction occurs. Just switch the partners. Just take the basic ions and pop them together correctly, like you're doing nomenclature, basically. Yeah. Any questions on that there? All right. So double displacement, absolutely no electrons being transferred. The charge of everybody on the left-hand side of the arrow and the right-hand side is the same. This is +1 here. That's -2 there. That's +1 there. That's -2 there. That's +2 there. That's +2 there. That's -1 there and -1 there. So everybody has the same charge. There's no electrons being transferred in this type of thing. Whatever their charges is and stuff, they stay on the same side. That's why these are not redox reactions. So there's no electrons being transferred in this case. We're just swapping partners in this case. Here again is what we just saw there. We basically just did a double displacement reaction. And again, we're just going to swap out and switch partners always. And that is always how you recognize it. There is no other reaction that has 2 ionic compounds to start with. Yeah. So you see on the left-hand side of the arrow, 2 ionic compounds, it's this reaction 100% of the time. Just like in a single replacement, there's only one thing that has that, something by itself with no charge and an ionic compound. So that's how you can recognize these things as what type of reaction is happening. And again, like I said, just switch partners, you'll be in business. Now, another type of reaction here is what is referred to as an acid-base reaction. This is also a double displacement reaction. This is an acid. This is a base. And whenever you take an acid and base together, you get 2 things. You get water and what is known as a salt. And a salt's a fancy word. I'm not sure how fancy it is, but it's a fancy word for just an ionic compound, a positive and negative guy basically together. So when you take a strong acid and a strong base together, you basically will make water and a salt. It is still a double displacement reaction. And how can I recognize it? Well, once again, positive, negative, going to switch partners here. So when H plus and OH minus come together, that is where the water comes from. And the water always comes from, in this case, with a strong acid or strong base, you always get the water from the H from the acid and the OH from the base. That is basically where the water comes from in this case. So H and OH gets you your water here. And what's left over is essentially where your salt's going to come from. That's K plus and Cl minus makes KCl. So whatever is left over will get you your salt part coming together. Just blew it. So there. Yeah. Plus our KCl. And again, our water and our salt in this case. So this is sometimes referred to as an acid-base reaction. This is also sometimes referred to as a acid-base neutralization reaction. It's called an acid-base neutralization reaction because pretty much what you're making in this case is the H from the acid plus the OH from the base is ultimately making water, yeah? And one of the three reasons why a reaction takes place, water being formed. So this type of reaction is basically making water, and that's the reason it's occurring. And you always get that when you have a strong acid or a strong base. Just like what we saw a second ago with our precipitation reaction, it made a solid, right? Which is, again, one of the three reasons why a reaction takes place is that solid forming. So acid-base neutralization reactions occur with a strong acid, strong base. Ultimately, you're forming water, which is ultimately the reaction that's occurring. H plus from the acid, OH minus from the base will always come together to make H2O, which is the water part of it. Any questions on that there? And again, no electrons being transferred here, still a double displacement reaction that's occurring in this case. The last type of reaction is a combustion reaction, and really a combustion reaction falls under a redox. So this falls under a redox reaction. There's two types of combustion reactions that you usually come across. I would say most commonly people come across what is sometimes referred to as like reaction. So an organic combustion reaction is you have an organic compound, and usually an organic compound contains carbon, hydrogen, sometimes oxygen. And you always have these three things. You always have O2 on the left, CO2 and water on the right. So if it is an organic combustion, you could pretty much count on those three things happening. Here's another one. This is propane. O2, CO2, and water basically here. Methane, propane, butane, those are all flammable things, right? And they basically do combustion type reactions along the way. So if you ever see any type of organic compound like this, and you need to know what comes on this side, it is a pretty safe bet. If you just write CO2 and water, that's what comes on that side of it in this sort of case. Now, there is another definition of combustion reaction, and really, technically speaking, the only thing that you need present for it to be a combustion reaction is on the left-hand side of the arrow, your friend O2. Yeah. So technically speaking, if you see O2 on the left-hand side of the arrow, it is a combustion reaction. So that's kind of the basic one. The type of combustion reaction most people are probably sort of thinking about and referring to, but technically O2 is all you need. So what does that mean? If we take an equation, a reaction like we saw earlier, which was magnesium plus oxygen, make some magnesium oxide. I'll put a 2 there, maybe a 2 there, yeah. This reaction, as we saw earlier, is 0, 0, +2, -2 electrons being transferred. That is a redox reaction, right? That is also, if I'm not mistaken, two things makes one thing, which could be classified as a synthesis or a combination reaction. And if I'm not mistaken as well, I also see O2 on the left-hand side of the arrow, which means this one technically could be classified as a combustion reaction. So as you can see here with this, for example, one reaction could actually classify it three different ways depending on what you're looking at. You should choose whichever way seems most appropriate for the situation. But technically, you could classify multiple reactions in different ways depending on what you're looking at. But ultimately, what we got going on is two big sort of umbrellas of classifications. We have our double displacement reactions. which again is always our double ionic compounds coming together and switching partners and making two new ionic compounds on this side. And this has a more specific classification of a precipitation reaction, which means you make a solid or a precipitate, and also has a acid-base reaction, which basically means you're going to make water. So under the big umbrella double displacement, you got acid-base reactions and precipitation reactions, which are more specific classifications. And under the big umbrella of redox, where you have electrons being transferred, you have all the rest of the reactions. You have your synthesis reaction. Two things make one thing. You have your decomposition, which is the opposite reaction. One thing makes multiple things. You have your single replacement reaction, where you have one thing that comes in and kicks out somebody and makes a new ionic compound. And you have your combustion reaction, which again is typically your O2 to CO2 plus water, if you have an organic guy, or basically just O2. So these are all about electrons being transferred. So big umbrella for specific classifications. And again, any question how to classify reactions. So you kind of look for those patterns as to how to classify them. And again, basically those three reasons is why these reactions take place. Any questions on that there? We're gonna continue on here. Next thing we're gonna talk about some important sort of calculations. And that is molar mass and Avogadro's number. So let's get into that here, I think. So the first thing we're going to talk about is the important sort of chemical unit, which is known as the mole. And the mole does have an abbreviation, and the abbreviation for the mole is actually MOL. Had to cut something off, so they cut the E off, it looks like. So that is definitely the abbreviation for mole. If you see that, it is very commonly confused by people when they see it. They think it's molecules. So sometimes they'll see MOL and think molecules. So definitely if you see MOL, it is moles. If they want molecules, pretty much in chemistry, they'll actually type out the word molecules. So if you don't see them type out the word molecules, it's most likely going to be moles. And again, that's a very common sort of error that a lot of people make. Now, much like in life, we do have sort of a word that represents a certain amount of something. So when we say, you know, we have a pair of something, that's known to mean that you have two of something. If you have a dozen of something, right, you got 12. You got a gross of pencils or something like that, that's 144. So again, the unit in chemistry that we use to represent a certain amount of something is the mole. And that's really the amount of substances that are contained in these elementary entities like atoms, molecules, particles, as there are in 12 grams of the carbon-12 isotope. If you remember, the carbon-12 isotope was the isotope they used to figure out the molar, the atomic masses of everybody on the periodic table. That was the isotope of carbon that they used. Come back to those, I think. Now, when we say we have a mole of something, as I mentioned before, it does represent a certain amount. And in the case of a mole, it represents basically that you have 6.022 times 10 to the 23. And that is what is known as Avogadro's number. And Avogadro's number is that 6.022 times 10 to the 23. If you have 1 mole of anything, that is the same as having 6.022 times 10 to the 23. Now, the units that go with kind of Avogadro's number does change. So, for example, they could be particles, they could be atoms, they could be molecules, They could be shoes. They could be pizzas. Right? The occasional shoe and pizza might come out in a question, but I would say probably most of the time with Avogadro's number, you're going to basically see the units of either atoms or molecules, depending on what you're dealing with. So the units can change a little bit with Avogadro's number, but the number stays the same. It's that 6.022 times 10 to the 23. We basically use Avogadro's number as a conversion factor. So we could write two conversion factors using Avogadro's number. We could say 1 mole of anything is basically 6.022 times 10 to the 23 atoms. Or just like any conversion factor, we could flip it around, use it the other way around, do a little dimensional analysis. 6.022 times 10 to the 23 atoms over a mole. And Avogadro's number, again, is really the conversion factor that allows you to go from moles to atoms or molecules or backwards. If you're starting with atoms or molecules, it is Avogadro's number that basically allows you to go either way. Now, Avogadro's number is a number that people learn and use, and sometimes use in the places where they shouldn't use them. So it's really important not to use Avogadro's number like in every calculation, just because like it's a number I remembered. So maybe I should just use it. So the way that you know that you should use Avogadro's number is you want to look for some keywords, and usually the keywords is either you're given a number that's in atoms or molecules, or you're looking to find a number that's in atoms or molecules. There's really no mention of atoms or molecules. You probably should leave Avogadro's number on the sidelines there and not use it in your calculation. But definitely either they give you a number that's in those units or you're looking to find one of those units, then somewhere along the way in your calculation, you're going to need to use Avogadro's number. So again, it is something that shouldn't be used, obviously, in every calculation. And really what I box here are usually, in most cases, the two keywords you're looking for as to, okay, somewhere along the way, I need to use Avogadro's number to do that conversion. Now, the term Avogadro's number, and as I mentioned before, it represents a certain amount of something. And again, if we go to anybody off the periodic table, for example, if I say I have 1 mole of hydrogen, that would have 6.022 times 10 to the 23 atoms of hydrogen, right? And again, that's going to give me two conversion factors I could use. 1 mole of hydrogen, 6.022 times 10 to the 23 atoms of hydrogen. Or again, you can flip it around, 6.022 times 10 to the 23 atoms of hydrogen over 1 mole of hydrogen. And you can basically do that conversion for anybody on the periodic table, any element, basically. If you have 1 mole of any element that's up there, you basically have that many 6.022 times 10 to the 23 atoms of that element. Now, we could also use Avogadro's number for something that's not just like an atom by itself. I could say in 1 mole of water, I would have 6.022 times 10 to the 23. And here the units would actually be molecules of water, because water is a molecule. So instead of just an atom by itself, like hydrogen, here we're dealing with molecules. So instead of atoms, we use molecules as a unit. And again, you could do the same thing. 1 mole of water gets you 6.022 times 10 to the 23 molecules of water. Or you could flip it around with the Avogadro's number up on top. Definitely also want to make sure you're using your exponent button, right? When you use this calculation, and 1 mole of water. So again, if we're doing something that's more of a molecule or a compound, we oftentimes will use molecules as the unit. If we're doing something just like an element from the periodic table, we will use atoms as the unit. Just like any conversion factor, you will not use both of them together in the same calculation. You'll do the opposites cancel like we talked about when we did dimensional analysis. So whichever one you need to get the unit to cancel out correctly would be the one that you want here. Now, probably a conversion that you're going to use more than any is actually molar mass. And molar mass has units of grams per mole. The number always stays with the grams part, and it's always 1 mole is basically the mole part of it. And the molar mass is the mass in grams per 1 mole of a unit. So for example, we can get the molar mass from the periodic table. It is the number that's underneath it. So again, if we look at hydrogen, 1.008, this is the molar mass. Now, earlier we used it as the atomic mass, and numerically speaking, the atomic mass in AMU, which is how we use it in that previous chapter, and the molar mass in grams per mole gives you the same exact number as what you see on the periodic table. So obviously a more usable unit is molar mass, because when you go to the balance, right, you weigh things out in grams. So that grams aspect is a more usable unit than AMU. But AMU and grams per mole is basically numerically the same. So you could say, for example, for hydrogen, in 1 mole of hydrogen, there is 1.008 grams. And basically the molar mass of hydrogen is 1.008 grams per mole is the molar mass of hydrogen. Typically speaking, when you go to the periodic table, depending on your periodic table, there may be a bunch of numbers there or less numbers. Typically it is 4 sig figs. When you pull a molar mass off the periodic table, it's typically how many significant figures that you want to go to. And we can use really molar mass as a conversion factor. And molar mass is the main conversion factor we use a lot to go from grams to moles, or backwards from moles back to grams. That is the molar mass from the periodic table, is what we use it for. We can use it just like any type of conversion factor. So for example here, we could say there is 1.008 grams of hydrogen and 1 mole of hydrogen, or in 1 mole of hydrogen, there is 1.008 grams of hydrogen. So again, you can take a dimensional analysis. The number always stays with the grams, and the moles is always 1 mole. We could also do this for something that is a molecule that has multiple things. So if you had something like water, what you would do is essentially go to the periodic table and just find all the elements that are there. So we've got oxygen, 16 there, and we have hydrogen, and you basically just add up all the parts. So if I wanted the molar mass of water, there's 2 hydrogens. There would be 2 times the molar mass of hydrogen from the periodic table, 1.008 grams per mole. Plus there is 1 oxygen from the periodic table there, plus 16 grams per mole. And again, that is basically our hydrogens, and that is basically our oxygens. And if we add it up, we get 18.02 grams per mole would be the molar mass of water. And again, the number goes with the grams part is per 1 mole. This is also just a conversion factor, basically. You could write 2 conversion factors, 18.02 grams per mole of water, or a mole of water is 18.02 grams. So again, molar mass is really just a conversion factor. You got a bunch of there, you add up all the parts, and that gives you how many grams there is per 1 mole. Any questions on that there? So for example, if I had C2H6, what would be the molar mass? So take a moment and calculate the molar mass of this guy. In grams per mole, we got hydrogen up there, carbon, 12.01, yeah. Always molar mass, periodic tables where you go, yeah, so that's always where you find it. Always the numbers on the bottom, that's going to be your grams per mole, or the molar mass of each of those elements. And again, 4 sig figs is basically what you want to pull out there. In this case, we're just going to again add up all the parts that we got going on. So we have 2 carbons, so 2 times the mass I find on the periodic table, which is 12.01 for my carbons. I'm going to add that to 6 times the molar mass here for hydrogen, 1.008 grams per mole. This will give me the molar mass here of this, which is 2 times 12.01 plus 6 times 1.008. I hit the right button there. That's going to give me a 30.07 grams per mole. Again, the number stays with the grams part. 1 mole is always it. Now, how does this help me, right? Let's say, for example, you were asked, like, here maybe. Let's say that you were asked, you know, how many moles, I'm sorry, how many grams are there in 0.255 moles of C2H6, right? So we want to know how many grams are there in 0.255 moles of C2H6. First off, when I look at that problem, I want to think about a couple of things. The first thing I want to think about is, do I use Avogadro's number here? No, because there again is no mention of molecules, no mention of atoms or anything like that. So we don't need Avogadro's number. This is a conversion from moles to grams, and always that conversion of moles to grams is the molar mass from the periodic table, which we just calculated obviously down here at the bottom. That gives us really two conversion factors. That gives us 30.07 grams per mole of our C2H6. Or again, we could flip it around, mole of C2H6 over 30.07 grams. What we want to do is just take a dimensional analysis approach to this calculation. We are given 0.255 moles of C2H6. Remember, opposites cancel, right, with dimensional analysis. So again, if it helps you, you can put it over 1. Now I could clearly see the moles of the C2H6 are up on top. To cancel them out, we need the opposite location, right, which would put them on the bottom. So we would want to use the molar mass in this form. And remember that the nice thing about dimensional analysis is you already know, hopefully math-wise, what you have to do. Everything on top gets multiplied, right? Everything on the bottom gets divided. So the moles here will cancel, and that will give us basically 0.255 times 3007. And that'll give us something like 7.6, we'll call it 7 grams of C2H6 in this case, yeah. So that is what we would use these for in this sort of situation. Any questions on that there? Now, also a very common mistake that people make when they go to do molar mass has actually something to do with what we were just talking about, which is balancing equations. So let's just say, for example, you had an equation and there was a 2 in front of this, right? And whatever the rest of the stuff is, it doesn't really matter, right? Does that 2 have any effect on my molar mass? The answer is no, actually. Yeah, so whenever you calculate the molar mass, regardless of whatever the coefficient may be in the balance equation, it is only based on the formula, and only the formula is the only thing you should use to calculate molar mass. We will actually use the coefficient shortly for some other calculation, but when you do molar mass, that is basically just the formula. That is why molar mass is how many grams there are per 1 mole, and 1 mole is just one formula of the thing. So that's a super common error that people make. They kind of incorporate the coefficients from the balanced equation into the molar mass. You should never do that. If you need molar mass, simply just the formula, calculate based on one of the formulas, and then you'll do it correctly. Any questions on that there? All right, so again, in this situation here, this is still the molar mass, yeah? So that is the proper molar mass for that guy, yeah? All right. Now, one last thing here to sort of tie everybody together, sort of Avogadro's number and molar mass and all that. If we have, for example, 1 mole of hydrogen, it would have 6.022 times 10 to the 23 atoms of hydrogen. and that would be equivalent to 1.008 grams. So they're all basically equal to each other. And same thing with our water, for example, if we had our 1 mole of water, that would equal our 6.022 times 10 to the 23 molecules of water, which would equal 18.02 grams. Yeah. So they're all equal to each other. And basically what ties them together is the moles. So what ties, for example, atoms to grams is moles. And again, that's Avogadro's number. That is molar mass. Or going in the other direction, molar mass, Avogadro's number. So it is the moles that sort of tie both of those units together. And again, you could use either molar mass to get the moles if you need to, or Avogadro's number to get the moles, or whichever way you're going. But the moles are sort of the thing that kind of ties both of those sort of units together. Any questions out there? All right. So as I mentioned before, we use Avogadro's number, and we also use molar mass to do these type of conversions. And I would say, again, molar mass probably more commonly carried out more than Avogadro's number. All right, so I want you to try a couple of these here, answer each of these questions, and we'll give you some numbers in case you can't see the periodic table. Helium is 4.003 up there, and zinc it is 6538. Why not? 6538. All right, take a few moments there and calculate up what it is asking for in each of those questions. Need Avogadro's number, right? There's no mention of atoms or molecules or anything like that. This is a conversion between basically grams to moles. And remember that conversion is the molar mass from the periodic table. So in this case, it's helium, and we'll pull off that number on the bottom there. And that basically gives us the molar mass of helium is 4.003 grams per mole. We could also use it again in dimensional analysis by just kind of flipping it around here. So we'll start with what was given to us, 5.46 grams of helium. Again, just take a dimensional analysis approach here. Grams are on top. Again, opposite's going to cancel, so we're going to use the one here on the right. That will give us moles of helium is 4.003 grams, just like normal dimensional analysis. Multiply the top, divide the bottom here. So we're basically going to divide 5.46 divided by 4.003. And that's going to get us here a 1.36. Again, the grams will cancel. Moles will be left over as our units. 3 sig figs based off the original number, basically, in this case. Any question on that calculation there? All right, so taking a look at the bottom, we got how many grams of zinc are there in 0.246 moles of zinc? Once again, that MOL is moles, not molecules. So again, here we have no mention of atoms or molecules, so we do not need Avogadro's number in this case. We just need, again, here our moles to grams, which is still the molar mass from the periodic table. So once again, since we're dealing with zinc, we would go to the periodic table. We would find our molar mass from it. That would give us a molar mass for zinc of 65.38 grams per mole. Again, we could use it as a conversion factor and flip it around if necessary. And now we'll just set it up dimensional analysis here, 0.256 moles of zinc. Once again, zinc is on, the moles of zinc are on top. So to cancel out, we will need the moles on the bottom here. And that's going to give us 6538 grams per mole of zinc. Once again, still multiplying the top, dividing the bottom. The moles will cancel. So we're basically just going to multiply these two together. 0.256 times 65.38. Both 16.7 grams of zinc in this case. Any question on that calculation there? All right, let's try another one here, I think. What is the mass in grams of one gold atom? Gold. Okay, let's take a look at this one. So here we're looking for the mass in grams of one gold atom. So that seems like a keyword there. Atom means I should use Avogadro's number somewhere along my way in calculation. I want to end up in grams, and I am definitely starting in atoms. So as we talked about earlier, again, the unit that sort of ties those two together are moles, right? And that means that I could go from atoms to moles using Avogadro's number, and then moles to grams using the molar mass from the periodic table. So that's sort of how I'm going to get there. And again, seeing that atom is a sort of a keyword that clearly I need to use Avogadro's number somewhere in the calculation. In this case, 1 mole of gold would equal 6.022 times 10 to the 23 atoms of gold. And again, that's Avogadro's number and really a conversion factor we're going to use. So we'll start with 1 gold atom. Again, just taking a dimensional analysis approach here. I got atoms up on top. That means I do need to put atoms on the bottom here in the opposite location for everything to cancel out. Atom of gold and a mole of gold in this case. Once again, I am multiplying and dividing. If you want to get an answer, you can at this point. But if I just look at units, the atoms on top and the atoms on the bottom are going to cancel. And I am left with moles, which is close to what I want, but I do want grams. So I do need to kind of go the next step there and get the molar mass from the periodic table. That again is going to come from the bottom there. And that means for gold, it is not what I just wrote there. 197.0 grams per mole would be my molar mass there for gold. That essentially is just a conversion factor we're going to use. And again, setting up with dimensional analysis, like we talked about a lot already, I could clearly see moles are on top. So I do need to put moles on the bottom so they go opposite of each other to cancel. So that would be a mole of gold is basically 197 grams of gold. Once again, we're still multiplying and dividing here. The moles on top and the moles on the bottom are going to cancel, and that's going to leave us grams left over at this point. We're basically multiplying everything on top, which is not much. It's all ones, except for the last one there. This is basically a 1, right? And we basically have 197. We're then going to divide it by Avogadro's number, 6.022 to the 23. Going to hit equals. And that's basically it. Everything else on the bottom is basically ones. That gets me 3.271 times 10 to the minus 22 grams. That's a really small number since we're talking about one individual gold atom, right? So it should be relatively small in terms of its mass. Any questions on that one there? In terms of significant figures in this particular case, I went with the molar mass, which is 4. Since 1 gold atom technically would be kind of like an exact number, you would count something like that if you could count it. So you could actually use any type of significant figures you want probably on this one in terms of the answer. Other questions on that there? All right, let's take a look at one more here, maybe so to finish up. Let's go with how many moles and molecules are there in 36.5 grams of N2O5. We'll do that. So nitrogen there is 1401 on the periodic table, and oxygen is 16. See what you come up with on that. Okay, so since we're getting to the end, let's take a look at this one here. And we're looking for two things, moles and molecules. And obviously molecules gives us a hint that somewhere there we're going to use Avogadro's number. We're basically starting at grams and we're going to eventually end to molecules. And again, moles is what kind of ties us between. In this case, we actually want the answer for that. So remember grams to moles, that is your molar mass from your periodic table. And moles to molecules or atoms is Avogadro's number, basically, to do so. So we're going to start with the first part here to go to this step, right? So to do that, we will need to go to the periodic table and get our molar mass of N2O5. Once again, we're just going to add up all the parts that we have in the formula. So there are, for N2O5, there are 2 nitrogens, each have 1401 from the periodic table. Again, for your nitrogens. And we have 5 oxygens, each are 16 grams per mole. Once again, from the periodic table. That's going to give us really a conversion factor to use, which is the molar mass. That's going to be 2 times 1401 plus 5 times 16, it looks like. That's a 108, call it 108, sounds good. 108.0 grams per mole, which is our molar mass. And again, really our conversion factor. So we can actually do the first part here. We'll take 36.5 grams of N2O5. Again, if it helps you, just put it over 1. That should clearly allow you to see grams are on top. So in this case, we actually have to use this in the reverse fashion, our molar mass. We do have to put the grams on the bottom and the moles up on top, so that the grams cancel. And we're actually going to get an answer in this case, since that was one part of the question. So we do want the answer. So we're going to go 36.5 divided by 108. And again, we are multiplying the top and obviously still dividing the bottom. That's going to give us 0.338 moles of N2O5 in this case. And that would be our moles, right? So at this point, we are now sitting right here in our transition, right? And first off, any question on the calculation there? Now we need to go the rest of the way, and it's Avogadro's number. Again, that's going to take us basically the rest of the way here. And in this case, it is 1 mole of N2O5 would equal 6.022 times 10 to the 23, which is Avogadro's number. These would be molecules in this case, as N2O5 is a molecule. So again, we want to use atoms as our unit here. We're just going to pick it up with the number here. And I'm going to use sort of the unrounded number a little bit. So I'm just going to kind of use just a little bit of those numbers. And again, that's the unrounded number that's on my calculator here, since we also want the last part. That's moles of N2O5. And again, doing dimensional analysis, moles are on top. That tells me moles need to go in the opposite location, which is the bottom here. And Avogadro's number in this case would go up on top. The moles are going to cancel. Once again, we're multiplying and dividing here. In this case, we're really just multiplying. I'm going to use the whole number, not the rounded number here in my calculator, 6.022 to the 23. I'm making sure I'm using my exponent button as well, times my 0.33796. Gonna get me here 2.04 times 10 to the 23. These would be molecules of N2O5. Now, clearly, if we were just looking for molecules, you could have just done the whole calculation together. But here, since we needed both answers, we broke it up along the way. Any questions on any of those steps? So, all right, we'll lay it up there